Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. In today's video, I want us to look at acids and bases, right? Yes, it's gonna be a longer video where now we have to explain everything thoroughly, right? So that we are in a position of getting maximum marks in our exam. Okay, let's just dive into it. So in acids and bases, I want us to start first by now looking at the theories. Okay, I want us on number one, look at the theories now. The theories where now we explain now a an acid or a base in terms of now how our previous scientists have named them, right? Remember, we have two scientists who we have three scientists rather. We have Arrhenius, we have Lowry, we also have Bronsted, right? But remember, Lowry and Bronsted, if I'm spelling that name correctly, they worked together. I hear they worked together thereof in the definition thereof, or rather in the discovery of that definition. So according to we're gonna start with Arrhenius here. Arrhenius, very important to get that name correct. Arrhenius. Then here we look at Lowry, the first scientist. Then we have Bronsted. Okay, these are two different names. Okay, this is the first scientist and the second scientist. So it was named after two scientists. Okay, Lowry as well as Bronsted. Then this one is just Arrhenius. Now, what did Arrhenius say? Arrhenius say now. Let's start with Lowry because now these ones are straightforward. Okay, Lowry said to us, let me say, Lowry and Bronsted said to us, an acid is a proton donor. This is what now Lowry and Bronsted say to us. Now, an acid, it is a proton donor. It means now it can donate a what? A proton. Okay. Remember what is a proton? Okay, let me do this. It is a proton, okay, donor. This is what you refer to as a proton donor. Then what is a base? A base is now, if the other one is a donor, the other one is a what? Remember, a donor is a giver, someone who gives, right? A base is a what? Base is a proton H plus. You don't need to include the H plus. Proton what? Acceptor. Okay, not receiver what? Just use the terms that they use there. Then now when you go to Arrhenius say now an acid okay, here an acid, here a base, okay. Arrhenius says an acid is a substance that now forms, or rather that produces hydronium ions, okay. Hydronium ions, what are hydronium ions? H3O plus. It produces hydronium ions in water, specifically where in water. Okay. Then now and says now to us a base is a what? Is now a substance, is okay. Substance that does what? That produces hydroxide. Okay. Ions. Let me do this. Hydroxide ions. Uh, okay. Hydroxide ions in okay, in water. Like that. Let me do this. I want to see something. Okay. Remove this. Okay. Okay, what are hydroxide ions? Let me try to zoom that out for us. A substance that produces hydroxide ions, which are OH minus, where? In water. Very, very, very important. Very, very, very important thereof. Okay. Now let us be in a position of saying, okay, we hear the definitions thereof according to Lori and all of that. Okay. Lori says now, if I might have my reaction, the first reaction, Lori says now, or rather Arrhenius says now, when I have a reaction in water now, okay, what do I form? Lori said now, okay, I'm gonna form what? Hydronium ions, okay, in water. An acid is a substance that forms what? Hydronium ions in water. Let's see. This is an acid, right? This is an acid, right? So now, if this is an acid, according to Lori, says this acid should do what? Should produce now hydronium ions where in water. But now Lori, what is Lori Bronsted theory says now an acid it is a proton donor, meaning now I'm expecting this acid to donate a what? A proton because it is an acid, right? To donate a proton to what? To H2O, okay? Then in that case, what will happen? H2O will now acquire a proton, but now it will be in excess. Okay, therefore, what will be left? What will be left here? It is what? Cl minus. Why? Because we have H plus and Cl minus in this compound, right? So if I'm taking H to the other side, what is that called? Like, can you see that? Then Then, can you see now this one follows now Lori posted theory as well as Arrhenius. Why? Because Arrhenius says an acid is a substance. It is a substance that does what? That forms what? Uh, H3O plus in water. Okay. Whereas now Lori posted says now an acid produces donates what's this? Hydronium ion or a H plus. Okay. Yes. So now this follows now both Lori and Bronsted. Now let's look at the second one. Now this one it is an acid now reacting in what in water. Okay. Now what if we dissociate now a base? What if we dissociate a base now? Okay. When we dissociate a base now, this will be only according to what? To Arrhenius, because Arrhenius says now our reaction should occur in the presence of water. Okay, so now this is Arrhenius because now a base we say it dissociates, it does not ionize or okay. An acid ionizes whereas a base dissociates. Okay, in water. Therefore, it will form what? It will form now ions. Why? Because now it will break this one into two. It's gonna be now sodium plus as well as OH, OH minus. And now, according to Arrhenius, it says now a base, it is a substance that produces OH minus. Where? In water. Okay. Now, let's look at this one where, remember, this one applies both Lori as well as Lori Bronsted as well as Arrhenius. But this one only states about Arrhenius. Okay. Let's look at the last one. Then, where we say, okay, this is the type of question where now we see a base, an acid, and all of that. Let's have HCl plus NH3. Can you see now there is no longer water, okay? If there is no longer water, it means you are talking about a Lori Bronsted. So now this is an acid. We know HCl it is an acid, therefore it should do what? It should donate a what? A proton. When it donates a proton, this one will be a what? Again, this is an acid. This one will be what? A base. Why? Because it accepts a proton. It is a proton acceptor. Okay, and that is the definition of a base. Okay, therefore it will form as what? NH3 will have another H ion, therefore, but it will be in excess. So we're gonna say it is a hydronium ion, like that NH4 plus what? What is left here? Left it is Cl. So Cl minus. Okay. Cl minus. Yes. Now, let me see. Okay. I wanted to talk about conjugates, but now I'll talk about them when we reach, yeah, we'll have that section. Okay, this is us just introducing the acid and base topic, right? Yes. Now, if we go now further on number 2, where now we discuss the relative strength. Okay, we further on go to number 2, where again on number 1 we discussed about the theories. On number 2, we further discuss about the relative strength of acids. We'll start first by relative strength of acids. What exactly do you mean by that? We're gonna say, okay, we have what we refer to as strong base. We have what we refer to as a weak base. Okay, we have what we refer to as a strong base. We also have what we refer to as a weak base. Weak base. So, I'm talking about acids here. Strong acid as well as what? Weak acids. Now, let's just divide that. Okay. All right. Perfect. Okay. Now, I want us to say now, let us define now exactly what do you mean by now a strong acid. Okay. So we say a strong acid, it is now a substance that ionizes. Okay. That ionizes completely in water. In water. To form very important high concentration. Yes, to form high concentration of what? Of hydronium ions. Very key. We are saying it's what? A substance that does what? Ionizes completely. It ionizes completely in water. Again, to do what? To form high concentration of hydronium ions. Okay? Form high concentration of hydronium ions. Now, if you go to a weak acid, it means now you're gonna say it is a substance. Okay? That ionizes incompletely in water. Again, it ionizes incompletely or it ionizes partially. Okay? Partially in water to form what? If it does not ionize completely, it means now it will form what? In water to form low concentration. Concentration of what? Of hydronium ion. Very important. It ionizes incompletely in water. Okay? To do what? To form now low concentration of what? Of hydronium ion. Okay? Okay. Now, another property that we need to know about these is that now we are still under acid and bases. Okay, this we are just continuing where you left off. We are saying now, okay, these ones now we have examples of strong base acids, right? So this is still under strong acids. These are weak acids. Okay. We are saying now, okay, under strong base now we have types of common strong acids such as HCl. Okay. H2SO4 as well as what? HNO3. These are the common now type of acids that they like to use. Okay, yes, common. I'm not saying these are the only ones. I'm saying they are the common one. Okay, on here the weak acids. Remember about oxalic acid, carboxylic acid from the organic chemistry. Those are weak acids, okay? Acids from organic chemistry are weak. Why? Because now we have what we refer to as uh, oxalic acid, ethanoic acid. Let me write them. Oxalic acid, I think it is written something like okay, COOH2, something like this maybe. Okay, this is a weak acid. If I remember very well. Okay, we have also CH3, COOH. This is ethanoic acid, right? Then we also have what? We also have HAF, hydrogen fluoride. We also have H3PO4. Okay, yes. These are the type that we come across. Then now we have what we refer to ionization constant of acids, Ka. Ionization constant of acids. Okay, remember on Kc we are saying it is equilibrium constant, right? But here it is ionization constant. So now we are saying in acids the Ka value is greater than 1, but in in strong acids the Ka value is greater than 1, but in weak acids the Ka value is less than 1. What do you mean less than 1, greater than 1? Meaning now if I'm having something like maybe 2 times 10 to the power of 5. This is greater than 1, right? But here maybe I have something like 1 times 10 to the power of negative 4. Can you see now negative 4 means it is 0.0001. Can you see that? Yes. So this is what we meant now by those. So now first thing first, the definition, relative strength. Again, strong acid, it is what, weak acid, it is what, example of those. Why do you need to know examples of those? Because now they can show you a reaction and say now, uh, is this a strong base or a strong acid, and give a definition for, give a reason for that. Okay. Then on number three, we're going to look at relative strength. Relative strength of bases. Relative strength of bases. Right? Yes. Now we're gonna create a table again as we did with acids. So we're gonna say here we have strong base. There we're gonna have a weaker base, right? Okay. Then now on strong base, we need to be in a position of defining what exactly is what is a strong base. Now the definitions between a strong base and a weak acid, a strong base and strong acid are not necessarily different, but now there are some few terms that we need to change. So instead of saying it is a substance that ionizes completely, we're gonna say now it is a substance. Remember what do bases do? Bases do not ionize, they rather do what? Dissociate, right? So I'm gonna say it is a substance that dissociates or dissociate, however the English that you pronounce it, dissociates incompletely, not incompletely rather, sorry, completely. Remember strong ionize or dissociates completely in water to form now, to form what? High concentration of what? In this case, you are not forming hydronium ion because this is not an acid. But in case, rather, we are forming what in order to form high concentration of what? Hydroxide ions. Okay? Hydroxide ions. Like that. Then when you come here, we just oppose some few words. A substance. You're going to say it is a substance that dissociates incompletely. Sorry. Incompletely. Where? In water. To form what? We are going to form low in this case. Why? Low what? Concentration of what? Of hydronium ions. Can you see now the very few things is that this one is a substance that it dissociates incompletely in water to do what? To form now low concentration of hydronium ions, right? Whereas this one now on the acids now it dissociates now completely. Where in water to do what? To form now a high concentration of hydronium ions. Very, very, very key. Very, very, very key thereof. Okay. Now let's look at type of examples that you might come across of bases, strong bases. So you know strong bases, they like this one, sodium hydroxide. They also use potassium hydroxide, lithium hydroxide. Okay. Those are the common ones they like to use. Okay. On this other side, they like using maybe ammonia, NH3, calcium carbonates. Carbonates are weak. Calcium carbonate, potassium carbonate, calcium carbonate, I'm repeating it. What is this? NaOHCO3, sodium hydrogen carbonate. I don't know. But yeah, these are common ones. These are common ones. I cannot even see here. I wrote NaOH. Let me see. NaOH 18. Okay, it's fine. Please consult with your textbook again and see the common acids and bases, weak and strong. This is just a review, Vela, on what I can remember. Then now, what do we say about now the ionization constant, Kb? Okay, of bases, ionization constant of bases. For a strong base, it will be greater than 1. Sorry. For a weak base, sorry, it will be less than 1. How interesting. Very, very straightforward, isn't it? Very, very, very straightforward thereof. Right. I want us to move now on number 4. Okay. On number 4 now, when we talk about now what we refer to as a dilute. Okay. A dilute as well as a as well as concentrated, because now we like to confuse dilute with now strong and weak. Okay. And it is a very, very easy thing. Concentrated. This is now dilute. Acids. Okay, let me just say concentrated versus dilute. Now let me be in a position of fetching a stick, rather not a what, a picture that will now explain now thoroughly to us. Okay, yes. Okay, now I have a picture now that will now use to differentiate between concentrated as well as dilute. Now I want you to take it like this. Now, assume that you have a very, very strong acid thereof, okay? Assume that you have a very, very strong acid, okay? Now, when you pour an acid now inside a 1 decimeter cubed volume, all right, or a 1 liter volume like that, okay? Here is that solution, right? Can you see? It has now, let's say now you put 1, 2, 3, 4, 5, 6, 7. Yeah. Can you see? Let's say these are 7 moles of that particular acid, right? Then can you see inside a 1 decimeter cubed, right? And now, and then can you see now you did this in a 1 decimeter cubed volume or 1 liter volume. Now, if you use the very same acid with the same number of moles, exactly 7 moles of the same acid, but now in a different container that has now 2 decimeter cubes in a 2 liter of water, that has 2 liter of water, what will happen? Do you agree with me that this one will be now more bitter? I do not want to say strong. This one will be more bitter than this, than which one? Than this one. Okay. So I want you to take it like this. if you have an Oros, okay, they like to use an Oros, and it's a very, very good example. An Oros, it is whatever, okay? In an Oros, if you put an Oros inside a 1 liter, let's say you put an Oros that is somewhere, let's say 50 milliliter of Oros, 50 milliliter of Oros in 1 liter. Okay, you'll feel that okay, this Oros is now sweet, right? Is now sweet. If it is sweet, it means now it is still concentrated. Why? Because you can still feel that sweetness. Okay. But now, if you put the very same amount of 50 milliliters of Oros, but now in a 2 liter, now that sweetness will now try to vanish away. Now you'll drink something like okay, it is there, the taste is there, but now it is not necessarily as effective as it was when you poured that into a 1 liter water. Okay, so now this is what we mean when we say it is concentrated. If it is concentrated, it means now the sweetness of it. Okay, I want to explain in terms of sweetness to avoid the word strong. Okay, the strongness of it. It's still a strong base. Okay, it is still a strong base, but now that was made to be dilute. You cannot make something strong become weak. No way. You can never make HCl to become a weak acid. No, it is only an it is always a strong acid. What you can do to it, it can either you dilute it more, you can make it more dilute. Okay, more dilute. Okay, so that now we try not to feel the bitterness. Remember, acids are bitter, okay? Or how they are. How are they? Oh, however the English. Again, we know that these are bitter. Okay. And another example. Another example. If you take soap, the soap that we use to okay, take the soap that you use to wash dishes, sunlight liquid. Okay, take a sunlight liquid and pour it inside a glass like this. The same amount. Okay, let's say you pour that there, and then you pour water inside this glass. Okay, and try to taste it. Okay, do not try it. But I do not want you to try it. But even if you were, okay, and then take a bigger glass, okay, and pour the same amount of sunlight liquid you poured in the first glass, okay, then now and pour water that will fill up now. Like here, you poured water that will fill up this cup, and also here, pour water that will fill up this cup. There are chances that on this cup, you will feel little taste that there is soap in there. But in here, definitely you'll feel that there is soap here. So this is what we refer to as what is dilute and concentrated. Okay. When it is dilute, it means now we have more number of or rather we have fewer number of moles of an acid or base per volume. Okay, let us be in a position of defining what is concentrated acid and now dilute acid. Okay, let us be in a position of defining that. Okay, so we are seeing a concentrated acid. Okay, when it is concentrated acid or base has what? Has more number of moles per unit volume. Per unit volume. More number of moles per unit volume. In 1 decimeter cubed, we have 7. Here there are still 7, but now as compared to the container that we are having, we refer to them as less because now can you see it does not make any effect or rather any stronger effect. So we are saying dilute acid or base now has what? Has less number of moles of acid or base. I forgot that there. Per unit, per unit volume there. Very, very, very important. Remember one thing, you cannot make something that is strong to become weak. That is a very, very key concept. Okay. Okay. Yes. Very, very, very key. Now let's move on to to number 5. Let's move on to number 5, where now we'll be now talking about now conjugate, or rather, let's say on number 5 we have acid base. Okay, acid base reaction. Acid base reactions rather. Now on number 1, or number A rather, let me say it is number A. On number A, let's talk about now conjugate acid base pair. Okay, conjugate acid base pairs. Very, very interesting. Conjugate acid base pairs. Now, I want to talk about a conjugate base of an acid and a conjugate acid of a base. Okay? Do not try to make this one difficult, okay? On first one, I want to say, okay, let me say, this is number 1. I don't know. Okay, this is number A, and this is Roman figure number 1. I want to talk about conjugate what? Base of an acid. Now we are having a what? Conjugate base, okay, of an acid. So now a conjugate base, it is now a substance that is produced after an acid has done what? Has donated an H plus. Can you see? It is a conjugate base. It is a base that is formed after what? After an acid has done what? Has donated. Let's define that. We're going to say a conjugate base of an ion. It is a what? It is a ion or molecule. Okay? Ion or molecule that remains when an acid has now donated a proton. Okay? I'm saying a conjugate base, it is now the remainder of whatever substance that will remain after an acid has what? Has donated a proton. The second part that you need to know is that a conjugate base will have a 1 proton less. Will be, actually, let me say, will be 1 proton less than the acid. Why? Because now, check. I'm going to do an example. It's fine. Check. If I'm having an acid here, okay? If I'm having an acid, HCl, reacting with what? With H2O now. Now, remember, this is an acid, right? It will do what? It will donate H plus. So this one becomes an what? An acid. This one becomes a base, right? What will be left on this acid? What will be left on this acid after it donates a proton will be what we refer to as its conjugate base. So now H2O will acquire H plus. It will form what? H3O plus. But now HCl will be left with Cl minus. So now this is the remainder of that acid, okay? The remainder of the acid will now be called conjugate base. Okay? Conjugate base. So now this is what we refer to as conjugate base pairs. Now an acid, after donating a proton, what will be left will be what? A conjugate base. Okay? You cannot say after an acid has donated a proton, then what will be left, it is a conjugate acid. No. Remember, they are conjugate acid base pairs. Okay? An acid will pair with a conjugate base. And now can you see now our conjugate base, it is 1 proton less. This one has a H, Okay, this one has no H, so hence we are saying it is what? One proton, one proton, one proton less. Can you see? Conjugate base will be one proton less than the acid. Very, very key. Very, very key. Okay, this is what we refer to now as a conjugate base. This will become a base, then this will become what? Conjugate acid, but we'll come to it. Okay, okay, yes, yes. Now, if I'm having something like of some sort, if I might have an example like this and say, let me see. Okay, let's have now on number 2, conjugate acid of a what? Remember, if you are conjugate acid, it means you are coming from a base, okay? Conjugate acid of a base. Now, this will be the remainder or what will be formed, all right? This will be what will be formed now when what? When a base accepts a proton, okay? There we said this will be what what will remains ions or molecule that remains when an acid has donated a proton. Remember, an acid will donate. Okay, when it donates, it will have something that is left. But here, on a conjugate acid of a base, it will be what will be formed when a base accepts. Remember, when I accept something, it means now I will form again. But when I lose something, it means I will have the remainder, okay, of whatever that I did not lose. Okay, so we're gonna say, you can say it's fine. Let's define it the same way as we defined the conjugate base of an acid. We're going to say now it is ion or molecule that remains or produced when a base does what? Accepts a proton. Huh. Then now it means now the conjugate acid will be how? The conjugate acid will be one proton more than the base. Really? Yes. Why? Because now it will be what will remain when the base accepts a proton. When you accept a proton as a base, whatever that you form there will have an extra hydrogen. Okay? So this is what you refer to. It say a conjugate acid will be one proton. Conjugate acid will be one proton more than the base. Let's have an example of that. Let's say now we have NH3 reacting with water to form now to us what we remember. This is a common base. Like you need to know, okay, NH3 it is a base, a weak base is find a base. So it means now this one it will accept a proton, meaning H2O will now be in this case do what? Donate. So now what will happen? What will happen is that when this one, which we say it is a base, meaning this one will become an acid. When it accepts our base, when our base accepts a proton, it will form now what? Hydronium ion. Okay, plus now the H2O now will lose and form us what? Hydroxide ion, right? Now I want you to see something. This what formed after a base has acquired a proton, it is what we refer to as what? A conjugate acid. Okay, this means will be a conjugate base. Remember, on the right hand side you have conjugate, right? So it means now if this is my base, it will have a what? A conjugate acid. Okay. If we rewind back and say what is a conjugate base? A conjugate base, it is the ion or molecule that remains when an acid has done what? Has donated an H plus. Okay. So this will be what? A conjugate acid base pair number 2, right? Yes. And see here, This one was a base again. Its conjugate acid will have what? Since well, this base accepted a proton, it means its conjugate acid will have a proton more. There, that is the truth that we see. Whereas here, this is an acid, right? So an acid, it loses or it donates a proton. So its conjugate will have a what? Will have a proton that is less because it donated one. Again, can you see now? It has an H that is missing there, hence the minus sign, right? The plus sign tells you that I'm in excess, then the OH minus tells you that I am short thereof. Similarly, if I can come here now that we know this will be a base when it accepts a proton, it will do what? It will form a what? A conjugate acid. Can you see this one? It is an acid, therefore an acid donates, right? It means its conjugate will have one hydrogen or proton less. Okay, then this one it is a base. Why? Because in this case it did what? It accepted again. So if it is a base and accepted, its conjugate base will have one proton more. When you accept something, your conjugate will have proton more. When you lose something, your conjugate will have something less. Okay. Now I want us to be in a position of saying, okay, we can see that you've been defining what and what, but I see here and water here, it is base, but water there, it is an acid. So what exactly is water? Is water a base now or an acid? Now that's where we come to a new concept of saying now, okay, on number B, under reactions, on number B, remember there we did number A, where we explained conjugate acid base pairs. On number B, we discuss now, we call what? Ampholyte. Ampholites. What exactly are ampholites? We say now ampholites are what? An ampholite, it is a substance that can act, okay, or react as either the base or an acid. That can act or react as either a base, either a base or the base, either a, okay, let me say a substance that can act, that can react as both an acid, no, a substance that can either react as, okay, a substance that can either react as a base or an acid. Very, very important. It is a substance that can either react as a base or an acid, depending on the reactant that it reacts with. Okay, so these substances we say they are amphoprotic. What do we mean by now they are amphoprotic? It means now they can either donate or lose proton. So they can either donate or accept a proton. Ampholite means now they can either react as a base or water or acid, right? But now amphoprotic substances now are substances that can either donate or accept proton. Okay. Now let's have common what common ampholites. The common one it is water, but this one everyone knows it. Water. We also have HSO4 minus. We also have what? H3, HCO3 minus. Okay. Let us have an example. Okay. Let us take HSO4. Okay. Let's say now I have HS. Okay. Let me say H2 SO SO4 plus uh okay plus water to form me what? Uh okay. Now, remember this, I know it is an acid, right? So if it is an acid, it will donate a what? A proton, like that. So if that happens now, this one will be H what? H3O plus. But now this one will be what? No longer H2, right? It will now be HSO4. But now we need to show that we lost a hydrogen by doing that minus there, right? And then now it reacts again. It reacts again with what? It reacts again with let me see. I want you to see something. It from that. Okay. HSO4 minus plus H2O again. Okay. Again. Can you see now it donated the first proton, but it can also donate another proton. So when it does that, this is also an acid. Okay, this is also an acid and it will now donate an H plus. When it does that, it will form us again H3O plus. Now I'm going to lose this H. When I lose this H, I'm left with SO4. But now instead of minus, I'm going to say now I lost two of them. Okay, now I want you to see something. Actually, let me take this down here. Maybe here. Here we have what? This is an acid, this is the base, right? Then it will form what? It will form a conjugate base. Okay, conjugate base, right? Then this one, it is a what? A base. It will form a what? It will form a conjugate acid. Remember, a conjugate base of an acid, it is a conjugate base will have what? Conjugate base of an acid. Remember, an acid, after it lost a proton, a conjugate base means now will have one proton less. Okay. Now a conjugate acid forms after a base is accepted, so it means a conjugate acid will have one more proton. So now I want us to be in a position of identifying now our our uh, our ampholyte in this case. Okay. Okay, on the first one we see that one is that one and what sharp. Here we see now this is what an acid, because it donates an H plus, right? This is an acid, then this becomes a what? A base. Why? Because it is accepting, right? Now our acid will form a conjugate base. That will be one less proton. Conjugate base. Why? Because it will have a what? Can you see? If after donating an H plus, it means now this one will vanish. When it vanishes, here it is, right? Can you see? No longer H. So hence I say that is a conjugate base. And this one now will accept and now form what? Conjugate acid like that. Now the question is which one between these reaction 1 and reaction 2 and reaction 3, it is an ampholyte. Okay, take it step by step. Start here, H2SO4. Can it be an ampholyte? No. Why? Because we only see it once. It only appears on reaction 1. Okay, an ampholyte should appear on reaction 1, on reaction 2. Okay, so we eliminate this one. We also eliminate this one because they appear once in this reaction. This one appear once in that reaction. Let's look now at H3O. H3O here, it is a what? An acid. Never mind the conjugate for now, okay? This one, it is an acid here. Also here, it is an acid. Can you see? On reaction 1, it is an acid. On reaction 2, it is also an acid. So H3O plus cannot be a conjugate, a what? An ampholyte. Let's look at H2O. H2O here, it is a base. On reaction 2, it is also a base. Can you see now? This also cannot be what? An ampholyte, because an ampholyte is a substance that can act as either a base or an acid. Let's look at this one. This one, it is a what? It is a base here, but there it is a what? It is an acid. So now we're gonna say therefore HSO4 minus. Therefore HSO4 minus is a ampholyte in this reaction. Okay, now I want us to be in a position of seeing how exactly are we saying that. If I reverse this reaction, this should be in a reversible reaction, by the way. Very, very important. It should be in a reversible reaction. If I take it from here and say, okay, this is a base and this is an acid, what will now my base do? What will now my base do? Remember, my base will try to do what? My right. So my acid will donate a what? An acid to that one. Right? Will donate H plus to that one to form as what? Can you see? I will have H. If I'm adding H on HSO4 minus, I'm gonna have H2 here, all right? But now when I gain, it means now I lose one electron. So it means now when I say H2 here, it means I should remove this because now I have acquired a what? A proton, hence forming us what? This. So can you see here it acted as a what? As a base, why it accepted a proton. But here HSO4 minus, it was the one that donated. Here it received, okay, it gained, but here it donated. Hence now we say it is a what? It is an ampholyte. Do not say when you see this question and they ask you which one it is an ampholyte and you see water here, you automatically say water. No, 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 no. Please always check, okay? Please always check. Okay. Now we also have what we call a diprotic, monoprotic, protic substances, and all of that. So when we refer to a monoprotic substance, okay, monoprotic substance, yeah, I think we have acid, monoprotic acid. It is a what? An acid that can donate one proton, which is our H plus. Let's see an example of an HCl. HCl, it is a monoprotic acid. Why? Because HCl can only donate one H plus. So can you see it only has one H plus like that. So when that one H plus is gone, it is done. So we're gonna form H3O plus Cl minus. So this is what we refer as a monoprotic acid. Now, when you look at the diprotic acid, diprotic acid, we're gonna say now it is a what? An acid that can do what? That can donate two protons. Sorry, protons. How? What are protons? These. So now, which one is that? When you look at H2SO4, here we did it in multi steps. Okay, it now reacted in multi steps because it first donated the first one and the remainder now donated the other one like that. So now H2SO4, when it reacts with water, I want you to see something. When it reacts with water, like that, each water molecule, it means now we're gonna need how many water molecule? Two water molecule. Why? Because now this one can donate 2H plus. Okay? It can donate 2H plus, meaning now we need two water molecule because if we have one water molecule, it won't react. So it means now we need what? Two water molecule so that each can acquire a proton. Okay? So that each can acquire a proton. When that happens, now what will form is that, okay, we'll have H3O plus, but 2 moles of H3O plus because each now what form the what? Um I'm lost now. So each mole of H2O has done what? Has acquired a what? A proton. Therefore, plus what? What will be left? When I take two of them, I'm left with SO4. But how many protons did I use? Two. I come here and say two minus. If I take this reaction and find the net, when I take this reaction and find the net, I want you to see something. The one, if I see you on the reactants here and I see you on the product on that side, I cancel you. Check. H2SO4 here, okay, it is alone. This one and this one will, can you see this one on here, their product reactants? Here they are products. So we cancel that off. You're going to be left with what? H2SO4. Then this one plus this one will form what? 2 moles of H2O. Can you see? Then this one and this one will form what? 2 moles of hydronium ions. Then this one is cancelled, and then we are left with SO4, SO4 minus. So this is the same reaction, but now done in multi-step. Can you see? So if I simplify that reaction, it's going to be what? H2SO4 plus, on reactants, I have 2 H2O. Can you see? It is this one and that one. Can you see that? Then on my reactants, I'm left with what? 2 moles of H3O plus. Can you see that I took 2 of those on my reactants? Also on my products. Then on my product, the last part, this one is off. Then I'm left with what? Okay, what happened there? Then I'm left with what? SO4. I'm left with SO4 2 minus. This is what I mean by that. So this is what you mean by diprotic, monoprotic acid and all of that, right? You can say triprotic acid, it donates 3. Like which one? I don't know if this one can donate. H3PO4, phosphoric acid. Yeah, I think it is can donate 3. Okay. Mm. But you are really asked about a triprotic. But know it, the definition does not change as such. Okay. Yes. Okay. Now let's have now the neutralization reaction. Okay. Okay. Yes, neutralization reaction on number. Let me see. This was number B of unfolite. Then let's see number C under acid base reaction and look at neutralization. Remember what are neutralization reaction? Neutralization reaction are now reactions of acid and base. Okay, remember to form what? Water and salt. To form now water and salt. Okay. Now let's look at the common one where we have what? Where we have ACN reacting now with sodium hydroxide. It's gonna form us what? Sometimes they might ask you to balance this or write a balanced chemical equation. Now this is H, it's gonna be H plus Cl minus. This is Na plus and OH minus. So what I want you to see is that the H will now want to move to OH, okay? Or rather the plus will want to combine with the minus, okay? Then the Cl will want to move with the what? Cl minus want to combine with the something plus. So it will form us something like sodium chloride. Can you see that? Sodium there, let me write it neatly. Sodium chloride. Here it is sodium chloride plus what? H2O. Plus H2O. Can you see that? Yes. So this is a strategy that you need to use now on knowing how the reaction will be now. Okay, it is a strategy that you should have learned in grade 10, but it's fine. Then let's have now again a second one, maybe HNO3, nitric acid, a strong acid also, plus now reacting with also sodium hydroxide. You want us to be in a position of knowing how to balance these equations. No, remember, I have to break down this one. This is H plus, okay? Then means it should be NO3 minus. Remember, this is a spectator ion, right? Then we have Na plus OH minus. What will happen? We know that this one will want to come here, right? Right? The Na will want to combine with the NaO3, so it will form as sodium nitrate, like that. Okay, water, it is in liquid. plus H plus and OH minus will want to form as what? Water they off in liquid. Can you see now how interesting are those? Now let's look at H2SO4, a diprotic. H2SO4. I want us to balance this reaction. Okay, for now it is unbalanced. We'll see. Now we have what? Can you see now this is H2? It tells you now we have 2 moles of H plus, right? 2 moles of H plus. And now these 2, remember, it comes from what? From the ion that this SO4 has. So SO4 has what? 2 minus. Why? Because now we know from grade 10 that if this was H plus and SO4, 2 minus. When they react, they do what? They swap their what? Their charges like that. This one comes there, meaning now they will form what? H will take these 2 down there, then SO4 will take this one down there, but we do not need to write it. Okay? So this is basically that. Okay? Yes. Then now, plus what? Plus sodium plus OH minus. Now, remember this one will want to react with 2 of those, okay? We want to react with 2 of those. So now it will be now in a position of saying, okay, when I hear you are here, where is it? Here you are here, right? So I need this one to react with that one. But can you see now this one, the OH here, it is single. Can you see? We only have what? We only have one OH, right? But we need how many OH? 2. So how can you do that? We can only do that by taking by doing this 2. When this one becomes, because I cannot add 2 only on that one. Remember, I should add 2 on everyone, right? When I add 2 on that one, it will now be 2Na, 2OH. Then now they are in a position of saying, okay, 2H plus 2OH, it will form as what? H2O. Sorry, it will form as what? H2O. But now how many reacted? 2 moles of that as well as 2 moles of OH. So it needs to be 2 there also. Plus, here what will happen? Here we'll say, okay, SO4 minus, okay, I can accept 2 whatever that you bring, 2 whatever that you bring. And this one can say, okay, I can give you 1. But now since when I have 2 in front, it means now I can have 2 moles of Na plus like that. So it means now they can be in a position of filling up these 2, okay? We do not need 2 here. Why? Because now we already have what? 2 minus. That shows you, or I can accept to bond with 2 of those. Okay, so it will be like, oh, okay. So it means now we are already fine. Then what will happen? I want you to see it like this. What will happen will now be saying, okay, Na plus now reacting with SO4, 2 minus. What will happen? The plus will go there, the 2 minus will go there. And that what will form as? That will form as what? Na2. 2, can you see? 2 is down there. 2 will come here, forming as Na2, then SO4, the 1 there. Oh, now we are focusing about the number. The 1 here will come here, which is 1. We don't need to write. So it will be Na2SO4, like that in aqueous. Can you see how interesting are these reactions? Now, let's check, is it balanced now? Let's look at H. H, we have 2 H here, or rather we have 2 plus 1, which is 3, okay? Okay. Is it 3? Oh, 4. Sorry. So remember here, it is 2. Okay. So here we have 2 plus 2 thereof. It is 4 hydrogens. Okay. On this side, I have 4 hydrogens. On this side, I have 2 times 2, which is 4 hydrogens, also very, very resonant. Now let's look at sodium. Sodium, it is 2Na here. Then here it is Na2. So it means now I have what? 2Na in this side, then I have 2Na on that side. Then I need to look at what? My oxygen. Oxygen, it is 4 plus 6. So 4 plus 2, it is 6O. Here on this side, I have what? 4O plus 2O, it is 6O. Then it means now everything, it is now balanced. Why? S, it is 1 there. acid is also 1 there. Everything it is in a state of equilibrium, balanced. Not only do we have that one that forms water and salt, but right now we do have that one that forms us now sodium carbonate as well as all of that, right? Let me do this one, the fourth one, so that they like this on multiple choice, okay? Where they have CH3, COOH, you can see plus sodium hydroxide. This one, they like it a lot, okay? They like it a lot. What will happen, this CH3, COOH will now form CH3, COO minus, then this H plus will be hanging alone, okay? Then on this side will be Na plus OH minus. You know what happens most. The plus want to combine with the OH. So will form what? Water. When this combine, it will form as what? Water in liquid. Plus now, but now, can you see now the minus will want to combine with the Na. So it will form as well something like NaC. So CH3 COO. Then to remove the minus, we now do what? Na. Then this is aqueous. How interesting is that? Then let's look at the reaction of carbonates. Okay, the reaction of carbonates, not only do they form now a salt and water, but now they also form what? Carbon dioxide. Okay, let us be in a position of looking at that. Let's say now we have HCl. Let me rewrite that. HCl in aqueous solution reacting now with what? Sodium carbonate. Okay, sodium carbonate. Now what will happen? What will happen now? I want you to see this will break now into many parts, which is H plus Cl minus. This one will be 2Na. Okay, plus then we'll have now carbon dioxide. So I do not see what is happening here. Um, mm, okay, we'll have here we have CO2. We also have O2 minus, like that. Okay, this one is fine. Just know it's gonna form you salt. Salt that you can form here, it is sodium chloride, water, and carbon dioxide. Sorry. Always the reaction of carbonate. The reaction of carbonates will always form what? Carbon dioxide. Okay. Very, very, very interesting like that. Very, very, very interesting like that. Okay. Yes. Now I want us to now be in a position of saying, okay, on number 6. Okay, we left on number 5, right? When we did acid base. 5 years. Now I want us to be in a position of saying, okay, on number 6 now, let us be in a position of looking at now what we refer to acid base titration. Okay, acid base titration. What is exactly titration? One should be in a position of saying, I need to understand what exactly it is, what it is titration. Okay, if I understand exactly what is titration, I should be in a position of knowing how to apply exactly what is titration. So a titration, it is now a procedure. Okay, a procedure now for doing what? Procedure for determining the amount, the amount of now acid or base in a solution by doing what? By determining the volume of of a known concentration concentration that will completely react with it. Now, I want us to be in a position of saying, okay, let us try to digest now this definition, because now it's a lot and you do not hear anything. Now, we are saying it is a procedure. All right, it is a procedure for determining the amount of acid or base in a solution. Okay, now it means now we do not know a certain amount of acid or base in a solution, but now if you want to determine that, what should we do? It is a procedure now of determining the unknown solution. Okay, by doing what? By determining the volume of a known concentration. Now you'll see what we mean by the known concentration, what we refer to as a standard solution. Okay, by determining the volume of a known concentration that will completely react with it. Meaning now, if I wanted to know, let's say now, okay, this now, okay, this now forces me to be in a position of saying, okay, on number B, let's look at apparatus that we use so that we should be in a position of understanding the definition of titration. Let's look at apparatus. Apparatus are now the setup that we use, okay? Let me quickly get in those apparatus quickly. Very, very, very good. Now, this is what we refer to as now our apparatus, okay? Our apparatus now we refer to as the tools that we use, right? Now, we have what we refer to as a retort stand, okay? That will now put this burette in place, okay? The burette is what we put, okay? Okay, let's now label this. This is a burette. Then now this is an Erlenmeyer flask or now conical flask. If you do not want to say Erlenmeyer flask, you can say conical flask. Okay. Yeah, but just know Erlenmeyer flask, then sodium hydroxide. Now, let's look at the definition of titration first. And now try to make sense of it. It says now, it is a procedure for determining the amount of acid or base in a solution. Okay. By determining the volume of a known concentration that will completely react with it. Now, the apparatus is set in such a way. In our burette, we have now the sodium hydroxide with known concentration, okay? This sodium hydroxide has a concentration. It also has a certain volume, okay? Now what we do is now, inside this burette, again, this is a base. Now we are trying to see the amount of acid that will now react with it, okay? So we want to know how much acid, okay, the concentration of acid that we need to react with sodium hydroxide so that we form a neutral solution. Remember, titration is a type of a neutralization reaction. So we are trying to neutralize this sodium hydroxide. Okay, we are trying to neutralize this sodium hydroxide, and it is a strong base, right? A strong base can only be neutralized by what? By a strong acid. So now we know the concentration of sodium hydroxide. We also know the volume of sodium hydroxide. But now we do not know the amount, okay? The amount of concentration of acid that we should pour inside of these so that now it becomes exactly titrated and exactly neutral, right? But now what we'll do, we'll take a burette and fill up as much as H2SO4 that we can possibly get from this until it reaches the reading here, okay? The burette has a reading there where it reads now the volume, okay? Now, the burette is reading starts from the highest value to the lowest value until now it reaches 0. So this is how a burette measurement is, right? So what will happen here will be now, okay, on our Erlenmeyer flask, we'll have a known concentration, okay? We'll have a known concentration. So here, inside here, we refer to that, we have a standard solution. The standard solution will be now on the Erlenmeyer flask. Now, what is a standard solution? Let us be in the position of defining what is a standard solution. Okay. A standard solution is a solution, okay, where a solution of now precisely known concentration, or exactly known what? Where's my concentration? So now a standard solution, it is a solution of precisely known concentration. It means now we know exactly the concentration that's in here, okay, and the amount of volume of that. But now we will use that standard solution to do what? To determine the concentration of H2SO4, okay? What will happen? What will happen now, we'll say, okay, this retort stand has something like a tap there, okay? What you will do to it, you will release it, you will release drops you will open it, right? Like a tap when you twist it or whatever the English there, when you twist it, what will happen? The amount of H2SO4 will now drop into the what? Will now drop into the Erlenmeyer flask, right? But now the question is, how will we know now when a remember burette measures the what? It measures the volume of a known solution. Okay. Uh not unknown solution, unknown substance. Now, as I open this tap now, what will happen? The H2SO4 will drop into the sodium hydroxide until. Now, the question is until when? Until when? Until now it reaches end point. When it reaches end point, what is an end point? An end point now, it is a what? The point in titration where an indicator changes color. Oh, an indicator changes color. But now we did not talk about an indicator. What should you do first? I'm taking this slow and slow so that you understand the apparatus. Okay. So now it means now before I can pour, all right, before I can open this tap here, I need to put a suitable indicator. Okay? Put a suitable indicator. Why? So that when I open this tap, and now I pour the H2SO4, I pour the H2SO4. Immediately when this indicator changes color, I know I have reached the what endpoint. I need to immediately close the what? Immediately close the tap of my burette. Okay. Then now that is when now we say we have reached what endpoint. Okay. The endpoint, it is now the point in titration where an indicator changes color, right? So now we close our tap. Then we do what? We have that. Titration reaction that we wanted. And during an experiment, as you open the tap and the H2SO4 is pouring inside the Erlenmeyer flask, you need to stir the Erlenmeyer flask, like shake it a little bit so that now we can see color change, right? Yes. What the question is, what will happen now if you miss the color change and pour more or few drops of H2SO4 after reaching endpoint? What will happen now is that the solution will no longer be neutral, but it will now be acidic. Why? Because now you no longer put an equivalent amount of what? Of acid that will neutralize sodium hydroxide. You have put more H2SO4, so our solution will be acidic, right? The purpose of now doing a titration, it is now to find a neutral solution, right? Now I want you to see something here. If the reading here it is 50, let's say now the concentration in this one, it is 0.5 mole per decimeter cubed. Then the volume here 30 centimeter cubed. Then the concentration here, it is unknown, but now we can determine the volume. Why? Check. It says it is a procedure determining the amount of acid or base in a solution. We are determining the amount of acid or base in a solution. In this case, it is a solution. It is an acid in a solution by doing what? By determining the volume of a known concentration that will completely react with it. Knowing exactly how much volume will react with it. So now let's say here it is 50, here it is 0. And now after reaching endpoint, the solution now reaches this. It is now here at maybe 34. Okay, this is measured in centimeter cubed. Now, initially your solution was 50, and now after endpoint was reached and you close the tap, it now reaches 34. Now, how much amount of volume reacted? Okay, or how much volume was poured inside the Erlenmeyer flask? Now, the amount of volume poured inside the Erlenmeyer flask will be now the difference now between the two. Okay, 50 minus 34, it is how much? When I do mathematics, it is 16 centimeter cubed. So it means 16 centimeter cubed of whatever unknown concentration reacted completely with this standard solution. Okay, now I need to find what? I need to find my concentration. How can I do that? That's where now we come to what? That's where now we come to where's that? That's where now we come to titration equation. That's where now we come to what we refer to titration equation. On number 7, we come now to what we refer to as what? Titration equation. Why now? Because now if I look at the example above here, and the titration equation goes like this: CaVa divided by CbVb, it is equal to now number of moles of acid divided by number of moles of base. You need this now, it is a concentration of acid, volume of acid, concentration of base, volume of base, number of moles of acid, number of moles of base. This now needs to be in a balanced equation. You need a balanced equation for this one. Now, volume can be of any measurement. Any measurement. What do I mean by that? It can either be centimeter cubed, decimeter cubed, meter cubed, or liters. As long as now what you substitute here in meter cubed, also at the bottom should be meter cubed. Centimeter cubed at the bottom, centimeter cubed at the top. How, like that, right? Now we need a balanced reaction between a sodium hydroxide and H2SO4. So we need to say, okay, let's have now sodium H2SO4 reacting now with what? With sodium hydroxide. You should know how to balance, because it is not always that the examiner will give you a balanced equation. Now this will react and form as what? Remember this one, we have 2H plus SO4 minus Y. We have 2 of those, right? Then we have Na and OH. Remember, we need 2 so that OH minus can have that plus here. So if I remember very well, it's going to be Na. Oh, sorry, SO4 minus, it is 2 minus here. I think I made a mistake there at the top. Where is it? SO4 minus should be 2. Oh, okay, it's fine. So SO4 minus will be 2 minus there, because this 2 comes from the top. Then now it will form as something like Na2 SO4 plus 2H2O liquid aqueous. Now this is a salt. The one that is formed with water, it is a salt, right? Let me see if it is balanced. No, it is not. 2 here. After 2 there, it is balanced. Cool. Now, remember what exactly I'm titrating. I'm titrating now an acid of HCl, or sorry, H2SO4 as well as what? The sodium hydroxide. How can I use this titration? Now, titration says now, I need to determine the concentration of what? Of acid in this case. Can you see? The concentration of acid in this case. Okay, there it is. Concentration of acid it is unknown. So I'm gonna come here and say, on my formula, I'm gonna say concentration of acid it is unknown, multiply by the volume of acid that reacted. The volume of acid that reacted it is 16. Okay, 16. How did we see that? If it started at 50 and ended at 34, we're gonna say 50 minus 34. Then it is the reacted one that we find 16. So it's gonna be what? 16. Okay. Can you see it is centimeter cubed? So it means at the bottom also I need to substitute centimeter cubed. Well, now what is the concentration of the base? Concentration of the base now, here it is. Concentration of the base, it is 0.5 mole per decimeter cubed. So I come here and say 0.5 multiply by, what is now the volume of the base? The volume of the base, it is 8. Can you see now I do not need to convert to decimeter cubed. Why? Because now here it is centimeter cubed. Also here it is centimeter cubed. They will all cancel off. Very, very good. Now, Na now, where do we find Na? Now, it is now the coefficient of now the base, sorry, the acid, the mole of the acid in the chemical reaction, as well as the mole of the base in the chemical reaction. So now, can we see now, H2SO4, which is our basis, so our acid has now 1, okay? So it means now the number of moles of acid, it is what? 1. Number of moles of our base, it is what? 2 from the chemical balanced equation. Therefore, now it's just a matter of doing what? Mathematical gymnastics. Ca will now be how much? I can say 1 divided by 2 multiplied by this whole part, which is 15. I get 7.5. Then 7.5 divided by 16. I got Mama Tag. 7.5 divided by 16. It needs now my calculator there off. It needs now my calculator there off. Therefore, I'll say 0.5 multiply by 15 divided by 60. I now get a concentration of 0.46875 mole per decimeter cubed. So this is what we refer now to as what? Titration type of question. Okay, this is what we refer to now as titration type of question. Now, what if now the examiner gave us another scenario there of that says now, let's have another scenario, say, during titration, during a titration, what happened during a titration? 6.5 centimeter cubed of dilute HCl neutralized, very, very important, neutralized or neutralizes. Remember I said the purpose of titration, it is to get a neutral situation. Again, neutralizes exactly 25 centimeter cubed of sodium hydroxide solution. Okay. If a concentration of the HCl solution is 0.2 mole per decimeter cubed. Calculate the concentration of what? Of sodium hydroxide. Now we need to know which one it is now which one is now a standard solution. Okay, remember standard solution, it is a solution of precisely no concentration. So which one is that? HCl of known concentration. So now it means now HCl, it is our standard solution. If now we were to create our apparatus, it means now we'll have our Erlenmeyer flask. I don't know how to draw, right? and all the return stands and all of that here. Then now holding now on a burette. Okay, let me try to bring that a little bit closer. Holding now a burette that drops a few. And remember, a burette has a what? Has a tapnyana there. I don't know how to draw, people, just bear with me. And then now, yes, okay, this is a burette. Remember, a burette now. Remember something of precisely no concentration will come to the burette, right? Because we know the concentration of HCl, and now this one means now we'll have what? Sodium hydroxide, and we also know the volume of this one. Okay, we also know the concentration of this one. Then they tell us that exactly the volume of this one neutralizes that, right? And remember, you need to, before you open your tap, what is it that you need to put first inside the LNMR flask? You need to put a suitable indicator. We will come to indicators. Okay, yes. And now they might ask you, what is a point in which now a titration? Okay, what is, give a term for endpoint or define endpoint. Remember, endpoint, it is a what? It is the point in titration where now the indicator changes color, right? So the point now where the indicator changes color, we refer to that as what? As endpoint. So we're gonna say, okay, let us be in a position of using our titration equation. But now, before we do that, we need a balanced equation. We are told that HCl reacts with what? Sodium hydroxide. Then it forms us what? We need to know. Can you see this is monoprotic, all of them? So it's gonna form you sodium chloride plus H2O. So now we say, okay, the titration equation says CN BA divided by CB VB. It is equal to what? NA divided by NB. What is now the concentration of our acid? The concentration of our acid is now 0.2 mole per decimeter cubed. 0.2 mole per decimeter cubed. What is the volume of the acid? The volume of the acid, it says now, can you see? Can you see? Read the English very, very precisely. It says now, during a titration, 6.5 centimeter cube of dilute HCl neutralizes exactly 25 mole per decimeter cubed of sodium hydroxide. Okay? If a concentration of the HCl solution is 0.2, like that, okay? So 6.5 of dilute HCl, it is now our volume. So it will be 6.5 divided by, what is a base? Concentration of the base is what we are looking for. Volume of this one, it is 25 centimeter cubed. What now is the ratio between acid and base? The reaction, it is 1:1. So now it is 1:2 divided by 1. Then it's just a matter of doing your mathematical gymnastics and becoming a mathematician thereof. How much do you get? How much do you get? Now I get something like, let me quickly punch that. 0.2 multiplied by 6.5, I get, yes. Then I need to divide that by 25. When I divide that by 25, I get something like 0.0552 watt mole per decimeter cubed, like that. Okay, this is the titration type of question. Now let's move on to number 8, where we talk about, now we've been saying, okay, an endpoint, it is a reaction in endpoint, it is a reaction in, it is endpoint, it is a point in reaction where now the indicator changes color. What is exactly it is an indicator? So now we have types of indicators. Indicators. Now on my indicators, I'm gonna say now I have what? My beautiful princess. My beautiful princess. Okay. What about my beautiful princess? My beautiful princess is studying what? Acids and base. Okay. I repeat, on indicators, I have what? My beautiful princess. My beautiful princess is studying what? Acids and base. Okay. Now, what is exactly my beautiful? princess. My beautiful princess says now the indicator, the first indicator now, it is what? Methyl orange. Okay. The second indicator, which is beautiful, it is bromothiamol, 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 bromothiamol blue. The third indicator now, which is princess, it is now phenolphthalein. Phenolphthalein. Phenolphthalein, however you pronounce it, okay? Now, this is what we refer to my indicators. I have three indicators. My beautiful princess, which is who? Methyl orange, bromothiamol blue, phenolphthalein, right? And now, my beautiful princess is studying acids and base. Studying what? Acidic, neutral, and basic. My beautiful princess, like that, right? So now, the values that you might get, you don't need to cram the values. So it reads between solution of 3.2 to 4.4, okay? pH, this is the pH, okay? pH scale. Then this one, it is neutral, something like between 6.0 to 7.6. Then this one, 8.2 to 10. You don't need to cram this, okay? What you need to know, it is that for an acidic solution, we need an indicator called what? Methyl orange. Okay? In acidic solution, we need what? Methyl orange. Why? And how can we get now an acidic solution? Let me remove this pH scale because we won't need them. How can I get an acidic solution? You can get an acidic solution when you now react what? When you react a strong acid with a weak base. When you react a strong acid and a weak base, your solution will be acidic. Okay? And now if your solution is acidic, now it means now your pH will be less than 7. So a strong acid and a weak base results in an acidic solution. And a suitable indicator for that type of reaction, it is what? Methyl orange. My beautiful princess is studying acid and base. Now, for a neutral solution can either be a weak acid. Please allow me to use abbreviations, okay? To say it is a reaction of strong acid plus weak base, okay? Therefore, the pH will be less than 7. Here, it can either be a strong base plus a strong acid or a weak base plus a weak acid. They need to cancel out each other, okay? So, strong or weak. Therefore, the pH here will be exactly 7. Approximation. Then the basic a solution to be basic, we need a strong base to react with a weak acid. Therefore, our pH now will be greater than 7. I repeat, my beautiful princess, methyl orange, bromothiamol blue, as well as phenolphthalein. Then now it is studying what? My beautiful princess is studying what? Acids and base. Okay, so it is acidic, neutral, and basic. This is now what we refer to indicators. These are the type of indicators we use. Now let's come here onto this solution that we had here. What is a suitable indicator here? Which indicator will not be suitable? We check. This is what? An acid. It is a what? A strong acid. This is a what? A strong base. So now strong acid and a strong base will cancel out, right? Remember, my beautiful princess is studying acids and base. Now, for neutral solution, it is this one, right? Because strong acid and strong base will cancel out and become neutral. So now, what is B? B, it is bromothiamol blue, so that my solution will be neutral. pH equal to 7. So this is bromothiamol blue. So it means now a suitable indicator for this particular case thereof is what? Bromothiamol blue. Bromothiamol blue. Please know how to spell those. Similarly, here it is a strong acid and a strong base. Bromothiamol blue, it is very, very important. Now, let's see at the color change on number 8. On number 8, we want to know, okay, if I add, okay, color changes. we need to know, okay, when I put bromothermal blue here, it will change a color to what color, okay? Especially if I add an acid, it will change to what color, okay? What if I I add a base instead? It will change to what, right? Remember when you use bromothermal blue, the color change that happens in acid will never be the same as the color change that occurs when I, instead of putting bromothermal blue and I put methyl orange. Why? Because now the color change will not be the same, so that you can be in a position of doing what? Of differentiating. So now the color changes. The color changes now, we're going to say we have now Mary, okay? Mary, baby, let me come here. Baby, not baby, baby, no. Baby, Tupac or Pac P, okay? Mary, baby, and Tupac. Can you see Tupac? Then you add P at the end. Do not say two pack. This one you do not want, pack. Then replace these two with P at the end, pack. What does this Mary Baby Pack P mean to us? Now, Mary Baby Pack P now are analogies that I use. They're often saying, okay, Mary Baby and Pack P says to me, these indicators are still the MVP, my beautiful princess. Okay, these are still my beautiful princess from that part. So this tells me this is a methyl orange. This tells me it is a bromothiamol blue. This is now phenolphthalein, phenolphthalein. Now this is an acid. This is an acid. This is an acid. So the analogy now says to us, methyl orange in an acid, very, very careful. Methyl orange in an acid, it turns red, but in a base, which we do not have, it turns yellow. Okay, I will write this. We say methyl orange in an acid and also a base. In an acid, it turns red. In a base, it turns yellow. Very, very key. Okay? Then I move on. Bromothiamol blue, in an acid, it turns yellow. In an acid, it turns yellow. But now in a base, it turns what? In a base, it turns blue. How interesting is this analogy thereof? Okay? Then phenolphthalein now, it says now, the phenolphthalein in an acid turns colorless. Okay? So phenolphthalein in an acid turns colorless. Okay, do not say no color. There will be a color. Why? Because now we do not know exactly the color of sodium hydroxide. What if it is pink? Okay, yes, it is colorless, but in base it is what? It is pink. Oh, how interesting is that? Let me repeat for the second time. I am saying now, my methyl orange in an acid, it is red. In a base, it is yellow, which we do not have an abbreviation for it. Again? So now, and here, bromothiamol blue in an acid turns yellow, but now in a base it turns blue. Okay? Phenolphthalein in an acid, it turns colorless, but now in a base it turns what? Pink. Last time. Methyl orange in an acid, it turns red, but now in a base it turns yellow. When you have this in an exam, Mary Baby Pack P, you are very, very concerned. Okay? Therefore, baby, which is bromothiamol blue, in an acid it turns yellow, in a basic solution it turns blue. It turns blue. Okay? Then Pack P, phenolphthalein in an acid it turns colorless, and then in base it turns pink. What does this mean? It means now if my solution is acidic, therefore my indicator will change to red. Okay, if my solution it is basic, it will turn yellow, like all of like that, like that. Okay. These are the type of things that you should be in a position of knowing and understanding. Okay, yes. Now let us be in a position of saying now, we have what we call now hydrolysis of salt on number 9. Hydrolysis of salt. One should be in a position of saying, what is a hydrolysis? Hydrolysis now is a reaction of water and salt. This is hydrolysis. Hydrolysis is a reaction of water and salt. So what does this mean? What does this mean? It means now, let me have now a reaction that says to me, if I have HCl, okay, on number 1, if I have HCl reacting with sodium hydroxide, it will form me what? Sodium chloride plus water. Now this is a salt that I want, and this is my water. Now what is hydrolysis? Hydrolysis now says to me it is a reaction of what? Of salt and water. Okay? Okay? Yes. Now I need to know this solution, is it basic now? Okay? The salt, this salt that I formed there, is it basic? Or the salt that I form, it is neutral now. Okay, how can I do that? I need to react this salt now with what? With water. Okay, to see if now this sodium hydroxide, sodium chloride that I formed is basic or acidic or neutral. I need to react it with what? With water. I need to take my salt and say, here is my water, and I need to react it with what? With water. Okay, when I react it with water now, it does not mean now this water now will have a formation of going back like that. No, this water will actually it will ionize. Okay, let's say this one will ionize in water. When it ionizes in water, it forms what? The ions, which is Na plus and Cl and Cl minus. Okay, yes. But now, when we reach this stage now, we say on this product, we need to take the one that is strong. Okay, that is strong. Can you see now? This is sodium chloride. It forms sodium plus and Cl minus. But now, the sodium here, the sodium comes from sodium hydroxide, which is a strong base, and the Cl comes from HCl, which is a what? A strong acid. Okay, so now it means now this one will undergo what? Hydrolysis, because it is an ion of a what? Of a strong base. Also, this one will undergo what? Hydrolysis, because what? It is an ion of a strong base. So strong acid. So now this now come into conclusion and say now, okay, this means now our pH it is exactly 7. Why? Because now this comes from strong something and strong something. So they will all ionize completely in water. Meaning now there's nothing that will be left. Okay, yes. Now let's look at the second one so that we make sense of what I'm trying to say. Okay, the second one I will have, let me have now on number 2, CH3 COOH. Here we already knew that the reaction is going to be neutral because now it's strong base and strong acid, but we need to prove using a relevant equation. So here it is CH3COO, COOH plus now sodium hydroxide. This we know it is a what? A weak acid. This is a strong Strong base. And we know that it means now our solution should be basic. Why? Because now the pH should be greater than 7. Why? Because now a weak acid and a strong base result in a basic solution. But now we need to find a balanced equation. Remember, when they say use a suitable, will the pH be greater than 7, less than 7, or equal to 7? Okay. Now they will say to you, use a suitable reaction. What you need to do, okay, this one you might be giving. This one, this reaction here that I'm writing here, you might be giving. So it's gonna be now, we're gonna form CH3 COONA plus H2O. This is our salt. We are interested in taking the salt now and doing what? And ionizing that salt and seeing what that salt results in what, okay? If your solution, okay, it's fine. I'll come back to that. This equation you will be given, but they will tell you, they will ask you, is the solution basic or acidic? Use a suitable equation to prove that. That suitable equation is what? Hydrolysis. What is hydrolysis? It is a reaction of this one in water. So I'm going to take this one and say CH3 COONA. Okay? I'm going to react it with what? With water. Okay? I'm going to react it with water. When I react it with water now, what will happen? So, when I react it with water, what will happen? This will now break into its components. What do I mean by that? It will break into CH3 COO minus. Remember, in a hydrolysis, I'm not trying to form a product. I'm trying to break this one into its components so that I become in a position of seeing exactly what is formed for me, okay? Let me quickly put my laptop into a charger so that we continue working nicely. Okay? Very good. Okay, so when I break this, it's going to be now into CH3COO minus plus Na plus. Okay? What I do on this step, I need to take one of these. Okay? Which one is that? I need to take the one that comes from a what? From a weak something. Okay? I need to take the one that comes from a weak acid or a weak base. Let's see. This one comes from a what? This comes from CH3COOH. This one comes from what? NaOOH. Which one comes from the weak something? This one, right? So this one comes from the weak. This one comes from an acid, strong. So I'll take the one that comes from the weak because it ionizes partially, not completely, right? So I'm gonna take this one that comes from the weak. What will I do to it? I will take it. I will say now, CH3. Where is it? I will take now CH3 COO minus, and now I'll react it with water in this case. Okay. In this case, I dissociated it. I ionize it. Okay. Ionizes. I first ionize it and then react it with water. When I react it with water, in this case, I'm no longer breaking it. I'm making it to react. When I react it, remember water, it is OH minus and H plus. So this H plus will want to come to that part. So it's going to form us what? CH3COOH plus what? OH minus. Now, the formation of OA minus tells me that now this solution, it is what? It is basic. The formation of OH minus tells me that, okay, therefore the pH should be greater than 7. Okay? Why? Because now there is a formation of OH minus there. Okay? I repeat, this reaction you will be given in the exam. You will be given. But you will be asked to see if now the reaction is basic, acidic, or now neutral. What you need to do, you need to take your salt and ionize it first in water. After ionizing your what's this? Your salt in water, it's gonna break into CH3CO minus plus Na plus, right? Then you check between the two ions that you have formed there, which one comes from a weak something, whether it can be a weak base or a weak acid. The one that comes from a weak something, you make it react with water. Okay? Then after reacting it with water, you'll see the product at the end. The ion that forms at the end will tell you the solution. Let's look at the third example, which is the third last example, under hydrolysis of salts. I'm going to say this was number 2, Roman figure number 2. On Roman figure number 3, let me now react. And I already knew this one will be basic. Why? Because now this is a weak acid and a strong base. Can you see now the pH should be greater than 7? Very, very good. So now let me react now. NH4 plus HCl, which is a strong acid, with now a weak base, NH4OH. Okay? NH4OH. It is a weak base. So I'm telling you, this is a strong acid, this is a weak base. What will happen? What will happen now in this case, now we will form now what we refer to as, they will give you this product, NH4Cl plus H2O. Remember, this is acid-base reaction. It always forms salt and water. But now we need to do what? Take our salt. Which one is our salt? This one. What should I do with that salt? I need to take this salt and do what? And ionize it first, okay? Remember, I ionize it first, okay? I first ionize my salt. I first ionize my salt. I need to indicate this I ionize so that you do not become confused. I first ionize my what? My salt. When I ionize it, it's going to be NH4 plus and Cl minus. Okay, plus Cl minus. Okay, then I come to that thing. I say this one comes from what? This one comes from NH4OH, and this one comes from what? HCl. Okay. Then remember, for me to perform a hydrolysis of what? I need to take the one that comes from a weak something. So which one comes from a weak something? This one comes from a weak base. This one comes from a strong acid. This one comes from a weak base. This one comes from a strong acid. I need to take the one that comes from a weak something and react it with water. Even here, we took the one that comes from a weak something and reacted with water. So you do not need to show me this, but you need to understand it. The one that comes from a weak something, whether base or acid, we take it and now we make it react with what? We make it react with water. Can you see in this case? In this case, this one was a negative. It had a negative ion. So it means now it was in a position of accepting a proton. Okay? But now this one, it is plus, meaning it is in excess, meaning it is in a position of donating a what? A proton. When it does that, we are left with what? With NH3. Because we took H plus, okay? NH3 plus what? When I add it there, we get what? H3O plus. The formation of hydronium ion tells me now that this solution, it is what? It is acidic, because I know H3O plus, it is associated with what? Acidic solution. So my pH, it is less than 7, it is acidic. Here, it is what? It is basic. It is basically that. Okay? It is basically that. First step, take your salt, ionize it. Okay? After ionizing it, take the ion that comes from a weak something and react it with water, and now you'll see the final product thereof. And it is true this is acidic because now it is a strong acid and a weak base. Okay? Let's talk about indicators. Let's remind ourselves which indicator is suitable in this case. The indicator that is suitable for a neutral solution, remember we have my beautiful princess, my beautiful princess. So my beautiful princess is studying acids and base. So now the neutral solution, neutral, basic, and acidic. So this one, it is pH 7, it is neutral, meaning now this we need bromothymol blue. Okay, This solution, it is basic. It needs what? This solution is basic. It needs what? Phenolphthalein. Right? This solution, it is acidic. It needs what? Methyl orange. How interesting is that? How interesting is that? Very, very interesting, right? Mhm. Now we go to the last part now where we seal everything. Where we seal everything. Now we have what we refer to as where is that? On number 10. Is it number 10? This was number 9. Hydrolysis of salt, number 8. Okay. This is number 9. This needs to be number 10. This needs to be number 11. Okay. So now on number 11, let us be in a position of saying, okay, let us have pH calculation. Okay. Now the pH calculation, it is not necessarily that difficult, but now you should be in a position of understanding that when we have a water, okay, reacting now with water. Let me say in actual solution. What happens thereof? One, remember, what is water? It is a type of ampholyte, okay? It is an amphoprotic substance. So it means this one might be in a position of donating and this one accepting. If that happens, what will happen? We will form now H3O plus what? Plus OH minus. This should be in a reversible reaction thereof, okay? But now, if this occurs in a reversible reaction, we need now to find the water ionization constant. Water ionization constant. What is water ionization constant? Water ionization constant is now what we refer to as Kw. What is happening? Is what we refer to as Kw. What does Kw say now? Kw says to me the concentration of this one. Okay, remember it is the concentration of products divide by the concentration of my what? Concentration of my reactants. Remember, this is what we did on chemical equilibrium. But concentration of water, it is equal to 1. Okay, it is always equal to 1 mole per decimeter cubed. So now it means now we do not need to write that one. So it means now the ionization constant of water, it is this. And this now gives us a constant value, which is now what? Which is now 1 times 10 to the power of negative 14. Okay? The ionization constant like that. Where at 25 degrees Celsius. Okay? This is what you need to know. Right? If now our solution is acidic, basic, or neutral. If now our solution it is acidic, it means now we have more number of hydronium ions than the what? The number of hydroxide ions. This means this is what we mean now by acidic solution. Okay, it has more concentration of hydronium ions than it has that of hydroxide ions. If now the solution it is basic, it means now the amount of H3O plus is less than the amount of OH minus. Or you can say the concentration of OH minus, it is greater than the concentration of H3O plus. Here you can say the concentration of OH minus, it's finite. Okay. For basic solution, remember the concentration of hydronium ions should be less than this one, or this one are dominant over that one. For a neutral solution, the concentration of this one should exactly be equal to the concentration of that one. And should be equal to what? If the product of this is equal to that, so it means this one should be 1 times 10 to the power of -7. Okay, yes. This is what we need to be in a position of understanding. Okay. Also now, be in a position of saying, if now I want to calculate the pH of something, I can say negative log of the concentration of that something, whatever the concentration that they have. I need to be in a position of saying, okay, I can get them like that. Okay. Let us be in a position of using this one. What if now I say, for an example, I react HCl with HCl plus, let's say, water, in that particular case, the off, and then it gives me H3O plus plus OH minus. I need to find the concentration of the pH of HCl. Let's say HCl has a concentration of 0.5 mole per decimeter cubed. If I need to find the concentration of HCl, it is an acid again. So it means now if it is an acid, we need to say, I need the concentration of its hydronium ions. How is that? Can you see HCl to hydronium ion? The reaction, it is in a ratio of 1:1. Okay? So if that is in a ratio of, sorry, not Cl minus, man. Not OH minus, Cl minus. I should be in a position of saying, okay, therefore, concentration of HCl, it is exactly equal to the concentration of H3O plus. Why? Because now they're in a ratio of 1:2, which is exactly 0.5 mole per decimeter cubed. Therefore, it means now I can be in a position of performing my pH calculation and say pH is equal to negative log of hydronium ion, like that. Then it will give me something like negative log. What are hydronium ions? Hydronium ions concentration is 0.5. Can you see when I do not substitute, I use a square bracket concentration, but now when I substitute, I use round bracket. Then I get something like negative log, negative log of 0.5. I get something like 0.3. Can you see? pH does not have units. Does pH have units? No, pH does not have units. Okay, yes, I get 0.3. And this should be reasonable now because now it is what? It is basic. Okay? Very, very interesting like that. Or what you could have done, you could have said, okay, instead of using this one, I know that concentration of H3O, no, it's fine. Okay, yeah. Then now we have what we refer to as POH. Like we started with pH. Now we have what we refer to as POH. POH, it is now pH of now a what? Hydro of bases. Okay, POH. So this is the same if I take now sodium hydroxide and I react it with what? I want to see what I can react it with. With this is a base and a acid. Okay, let me use this one. NH3. It's gonna form me what? Remember, this is a base. It's gonna accept a proton, so it's gonna form me NH4 plus OH minus. Okay, yes. Now, if they said calculate the pH here of this solution, what you'll have done, what I recommend you to do is say, okay, I'm working with this and it forms me OH. And I know the formula for pH, it is what? Formula for pH, it is what? it is pH is equal to negative log of what? Of OH minus of H3O plus. Okay. But now in this case, my product it is OH minus. How can I do that? I can say it's fine. Let me say I have a concentration of this one, which is 1 mole per deciliter cubed. I'll need to say, okay, I need the OH minus, the concentration of OH minus. The concentration of NH3 is equal to the concentration of OH minus. Why? Because now they are in a ratio of 1 is to 1, which it is equal to what? 1 mole per decimeter cubed. Okay. Then I can say, okay, let me calculate POH, which is equal to negative log of what? OH minus. Okay. But now, can you see the question said now to me, calculate what? pH. Okay. Now, but now I have what? I formed OH minus. I'll say, okay, it's fine. It does not make a big deal. I'll just say it is negative log of what? OH minus, it is how much? 1. Then I get how much? Negative log of 1. Let's not use 1. It gives me 0. Let's not use 1. It gives me 0. Let's use something like 0.15. 0. Or 0. Let me see 0.3. Right. 0. Okay. Yeah, let us use 0. Maybe 13. Okay, let's use 0.13 as we believe. 0.13 mole per decimeter cubed. So it's going to be 0.13 like that. Then how much do you get? Remember what you are getting, it is what? POH. Okay? It is equal to negative log of 0.13. You get a standing number of 0.886. Okay? Now, after getting 0.886, remember the question was calculate the what? Calculate the pH. Now, there is this formula that I like that says now pH plus POH is equal to 14. Yes, meaning now if now I have POH, if I need pH will be 14 minus what is POH? 0.886. Therefore, my pH will be 14 minus my answer will be now 13.111. Okay, I don't know what to say. 13 let me say 0.886. 13.114. This will be my pH. And now, can you see my pH? It is very reasonable that it is 13. Why? Because now the solution now that I formed was basic. Now, another alternative method that you could have opted to use was that, okay, use the second method that says to me, I know that I have Kw, which says the concentration of hydronium ions plus the concentration of OH minus gives me what? 1 times 10 to the power of negative 14. This you are given on your what? Then say to me, I already have the concentration of OH minus, which is 0.13. Therefore, I can say, okay, let me find the concentration of H3O plus, because now at the end of the day, I want my pH. So let me find the concentration of H3O plus. Here I have the 0.13. Then here it is 1 times 10 to the power of negative 14. When I punch my calculator and say concentration of H3O plus, it is equal to 1 times 10 to the power of negative 14. Divide now by 0.13. How much do I get? I get something like 7.6923 times 10 to the power of negative 14. Okay? Take at least 4 decimal because this is not the final answer. Then, okay, if I'm done, I can say, okay, then I can calculate my pH, which is negative log of what? Negative log of hydronium ions. Right? Therefore, how can I substitute? I can say negative log of what is H3O plus concentration? It is 7.6923 times 10 to the power of negative 14 thereof. Then I punch this on my calculator. More or less, I should be getting the same value. I say negative log of my answer. Thereof. I get something like 11.114. Or to 2 decimal, it can just be 11.11. Sorry, man, 13.114. Can you see now the steps that are followed here? You can start by saying, okay, I know I produce OH minus. How about I find the concentration of OH minus and come here to POH, okay, instead of pH. And now I know at the end, getting POH is not the final answer. Why? Because I need pH. pH plus POH, I know, right? It's equal to how much? It is equal to 14. Okay, therefore I know this one. I can transpose that one and get now my pH. Or someone might say, I know ionization constant of water, that if I have concentration of OH minus, okay, concentration of OH minus and the concentration of, concentration of H3O plus multiplied by concentration of OH minus, give me what? Give me 1 times 10 to the power of negative 14. So it means now if I have already found here the concentration of OH minus from the mole ratio, what can I do? It means now I get what? I get concentration of H3O plus multiplied by now 0.13 that I know. Therefore, it's equal to 1 times 10 to the power of negative 14. I do my maths, I get concentration of H3O plus. Then after getting it, I come back to the solution of story to the pH is equal to formula. Okay, then I get an answer. And I want you to remember something. If now I have H2SO4, it produces 2 moles of hydronium ions. Why? Because now it can donate 2. So it means now the ratio is 1:2. Meaning now, if this one has a concentration of 0.1, this one will have a concentration of 0.2. Okay? This is what we refer to as diprotic elements. Unlike this one, which is 1:1, and the concentration of this one is equal to the concentration of that. Here, HCl to H3O plus. No, this one will say now concentration of H3O plus, it is double the concentration of HCl. Why? Because can you see the ratio is 1:2 thereof. So if I have concentration of H3O plus, I need 2 concentration of H2SO4. Similarly, if I have calcium carbonate like that, then it's going to form me 2 moles of OH minus. Why? It can donate to what? 2 hydroxide ions. So it means now the ratio is 1:2. If I have 0.4 here, I need to have 0.8 there. What does this mean? It means now the concentration of OH minus, it is equal to double concentration of calcium hydroxide like that. How interesting is that? So thank you very much, folks, for joining me. I know it was a long session, this one. But yeah, acid-base, very interesting topic that is assessed in grade 11 and 12, okay? So actually, this one, you only find it in grade 12, okay? This one is for those doing grade 12. From here, it is only grade 12. Only grade 12s, okay? But from here, from the indicators going up there, that is for both grade 11 and grade 12. Both grade 11 and grade 12s. Okay, yes. Just that in grade 11, we just add few things, okay, such as pH calculation. I think also in grade 12, you do pH calculations. Actually, it is for all. It is for all. Actually, it is for all. Because I think sometimes in grade 11, they are in a position of calculating pH. Things have changed now. So yeah, it is for both grade 11 and 12. So thank you very much, folks, for joining me on this topic. I hope you enjoyed it. Thank you.